Okay, so today we're going to talk about some titrations, or with specifically looking at acid-base titrations, right? Because not all titrations have to be acid-base, and in fact, I think this year we'll probably do a titration that is not acid-base, but in this case, we're going to be focusing on acid-base. So exactly what is a titration is probably the first question we should be asking, and that is slowly adding one reactant to a solution of another reactant while monitoring equilibrium concentrations, right? And so again, keeping in mind that specifically if we're talking about acid-base, that's usually that we're looking at pH, and we will monitor that with a pH probe. And what this can be used for, so two things that we tend to use this for is determining the concentration of one of the reactants, so that's a pretty common one that we will definitely be doing, and then determine the equilibrium constant for the reaction. So that's another way that you can use this. So there are a couple things that we should look at because strong acid, strong base titrations work a little different from weak acid, weak base titrations. And also remember that these things go basically the opposite for if you're doing strong base with strong acid or weak base with strong acid. So basically just flip these. The graph here would look similar except go the opposite way for anytime you're using a base acid titration instead of an acid base titration. Okay, so looking at this, there are 4 points on this graph that are labeled. The first point is where we have the initial pH, and this is determined by the concentration of the strong acid because no base has been added yet. The second part, where base has been added, where the pH is determined by the concentration of acid not yet neutralized, right? So we're going to have to do a little bit of stoichiometrying there to figure out the concentration of acid that's left. 3 is the equivalence point. And for a strong acid, strong base titration, right, the pH is going to be 7 at the equivalence point because equal amounts of acid and base are present and so therefore have neutralized everything. And for a strong acid, strong base titration, the pH changes very rapidly near the equivalence point. As you can see on the graph, the line is pretty much vertical there. And then in 4, right, that top section of the graph there, that's where you have excess base, and so you can determine the pH at that point by looking at the concentration of the excess strong base. So if we're looking to do some calculations with this, which of course we are, why would we not? We can ask a question like, what is the concentration of an HCl solution if 35 milliliters of 2 or 0.2 molar sodium hydroxide were needed to bring 10 milliliters of the acid solution to the equivalence point, and then what was the pH of that initial solution? So the first thing we're going to start out with is looking at the reaction, and that is hydrochloric acid reacting with sodium hydroxide to form water and sodium chloride. All right, so that's what it's going to look like. And in this case, because both of these are strong, we're not going to treat this as an equivalence or an equilibrium type situation. So we're not going to worry about writing an equilibrium expression. We're just going to jump to our stoichiometry, right, where we know that we have 35 milliliters of our hydrochloric acid solution, or I'm sorry, our sodium hydroxide solution that was used, right? So that's our NaOH, our 35 milliliters or 0.03 liters. We know it has a concentration of 0.2 moles per liter, right? So we put that information in there. When we look at our balanced equation here, we see that our mole ratio is 1:1, and that we had 10 milliliters of our initial solution, right? So 0.1 liters, which means that the concentration of our solution to begin with was 0.7 molar, right? So that's the initial concentration of hydrochloric acid. And we take the pH of that, we take the negative log of that number to find the pH, right? And we get a pH of 0.15. And there we go. That is how we answer that question. Pretty simple, very straightforward. We find the initial concentration of our acid. We take the negative log of it. That's all there is to it. Okay, now this graph looks similar to strong acid, strong base, but there's one difference in that, right, this region is much smaller and you have a gradual increase in pH as you are adding base. Right, so the initial pH is similar. We're going to, but in this case, use the Ka with an equilibrium expression to calculate the pH, because again, we're working with a weak acid, which we treat that as an equilibrium type situation. The midpoint, right? So this is the midpoint, and that's when enough weak acid has been neutralized that there are equal concentrations of the acid and conjugate base. And if you remember our Henderson-Hasselbalch equation, right, like this, when these concentrations are equal, right, this section crosses out, we get pH equals pKa, and so that's something good to remember, that at the midpoint of any weak acid, strong base, or weak base, strong acid titration, at your midpoint, pH is equal to pKa. Equivalence point, so we still have equivalence point. It is still the same thing. It's when all the acid has been neutralized. But in this case, due to the fact that weak acids have strong-ish conjugate bases, right, the pH for this titration is above 7, right? So it is basic at the equivalence point because of the conjugate base, right? And so in this case, conjugate base and its basicity cannot be ignored. And then, of course, after the equivalence point, right, this is still exactly the same. There is excess strong base, and so the pH is calculated based on the strong base concentration. All right, so if we wanted to do some math with this as well, we might ask a question like, what is the pH at the equivalence point in the titration of 50 milliliters of 1 molar acetic acid with 0.1 molar NaOH? So the first thing we're going to look at is the reaction between acetic acid or acetic acid and sodium hydroxide, right, where we form water because it's a neutralization reaction and a salt, right, NaC2H3O2. Now, keeping in mind that the Na really doesn't matter and that we're interested in this anion, which is the conjugate base of this acid, and that's going to be important as we go forward. But to start out, right, we're really only interested in the this reaction because we need to know how much of this NaOH is going to be required to neutralize this and get it to the equivalence point. And if we look here, right, we have balancing numbers of 1 everywhere. And since these are the same concentrations, right, and this is a 1-to-1 reaction, we're going to need the same number of milliliters of this strong base to neutralize this weak acid, right? So we've got 50 milliliters of our strong base. And so what we do, we're going to find the molarity of our conjugate base, remember this one. And so we have the moles of our acid, right, which is just 0.05 liters times 0.1 mole over 1 liter, giving us 5 times 10 to the negative third. And remember that when we're looking at equivalence point, we have this volume of our base that we've added and this volume of our original acid, making 100 milliliters or 0.1 liter to give us a concentration of our conjugate base at the equivalence point of 0.05 molar. So great. Now we know the concentration of our conjugate base at the equivalence point. And we can move on to looking at this reaction, because at equivalence point, right, once we stop adding base, this is the reaction that we're going to be concerned about, where our conjugate base is reacting with water to form a conjugate acid and hydroxide, which is what we're really going to be looking at. So the first thing is to set up a equilibrium expression, which you will notice in this case is Kb, because we're looking at the base. We have our conjugate acid, our hydroxide, and our conjugate base all in there. And we're going to need to figure out Kb as a first step, remembering that Kw equals Ka times Kb, or Kb equals Kw over Ka. So now we know Kw, right, as 1 times 10 to the negative 14th, and based on either looking it up in your book or previous examples, we know the Ka of acetic acid to be 1.8 times 10 to the negative 5. So doing these calculations, we can figure out that the Kb for acetate is 5.6 times 10 to the negative 10, right? The other things we can look at are knowing that this is the Kb and knowing the concentration of this is 0.05 molar, right? We can already make some assumptions that when we go to put x's in here, right, and we would have 0.05 minus x on the bottom, right, this number is definitely less than 5% of our concentration, which means we don't need x, right? And so as we go to fill in our numbers, right, we can just write it like this, where our Kb, right, that we just calculated is equal to our concentration under x squared, right, because we had our HCHO here and our OH, right, and because this is all 1-to-1 up here, they will be the same concentration, so we can say x squared. When we rearrange this to solve for x, it's going to look something like this. We're taking the square root of Kb times the concentration of our conjugate base, giving us a concentration of 5.3 times 10 to the negative 6th for our hydroxide, right? Because that is what we are concerned about. We're concerned about our hydroxide. So using this number, right, just like with hydrogen concentration, we can calculate a P version of this, or POH, right, which gives us a POH of 5.28, which is great, but we're not concerned with POH, right? We want to know pH at equivalence point. So if you recall that POH plus pH equals 14, then we can just say that 14 minus 5.28 gives us a pH of 8.72, and that is what we want. So we have now come to the end of that example, and that was a lot of work, I know, just to find the pH at the equivalence point, but that is the process for a weak acid, strong base titration, finding the pH at equivalence point. Okay, so polyprotic acids, right? So those would be mostly weak acids with strong base. You'll notice that this looks much like a weak acid, strong base titration, except that there are multiple midpoints and multiple equivalence points, right? But these work exactly the same. The only difference is that there are multiples of the midpoint and equivalence point. In fact, there is one midpoint and one equivalence point per acidic proton. All right, this particular diagram shows a polyprotic acid with 2 hydrogens. So it would be H2X, whatever X is, and that is what the titration of polyprotic acid with a strong base would look like. And you still calculate everything the same way. You just would calculate based on which area you're using a particular Ka, right? So this would be like involving Ka1, this would be involving Ka2, right? Or more likely, if you're looking at equivalence point, Kb1 and Kb2. So, as I said, the other way besides using a pH probe that you might be figuring out equivalence points and points is using a acid-base indicator. So for strong acid-base titrations, right, this isn't as much of a worry because there's a wide range of indicators that can be used as the change in pH at equivalence point is so large and happens so quickly, right? We don't have to be as picky about the indicator we use. However, for a weak acid, strong base titration, we have to be a little more careful about the indicator we use because they change color at different pHs. So your book gives some examples on page 733, 734, but there are a lot more indicators than just the 2 that they talk about. And in fact, here is a little example of the 2 that they do talk about, and we can look at the difference. So if you look at this line, right, this is the strong acid, strong base titration. Either of these indicators will work because both of them change color in this really steep section here, right, where the pH is changing so quickly, it's not going to matter which of these you use. Both of them will essentially tell you where the equivalence point is, more or less, because you need so little base to push the acid or push the pH of the acid way up here very quickly. With the weak acid, right, this line, on the other hand, right, methyl red, because of where the pH changes, you would change color around the midpoint, right, instead of the equivalence point up here. Right, so phenolphthalein would be a good indicator for this particular weak acid, weak base titration, whereas methyl red would not because it changes color way before the equivalence point pH, whereas phenolphthalein changes color right around the equivalence point pH, right? So like I said, for strong acid, you can use either of them. For weak acid, methyl red will not work because it changes color around the midpoint rather than the equivalence point. Okay, so that is titrations. I will see you in class.